Good morning, students. So in the previous class what we have discussed is about Coulomb's law, electric field intensity and electrostatic force. Okay, so we have seen the definitions, mathematical model for the same, and we have derived a mathematical model for vector representation of Coulomb's law and electrostatic force. So in this class, this is the agenda. So the first agenda is field due to many point charges, and field due to line charge, field due to surface charge, and electric field due to volume charge. So we are going to see all the 4 topics in this particular session, and along with the mathematical models for these things. Okay. So let us recall what we have studied in the previous. Electric field intensity. Electric field intensity is the force experienced by a unit positive charge when it is placed inside the electric field, given electric field, that is given by E is equal to Q divided by 4 pi epsilon naught into R square, right. So this is what we have seen in the previous class. About Coulomb's law, we have derived the equation. Okay, by using those concepts we have to derive the mathematical model for these 4 concepts in this particular session. So let us take the first topic, field due to many point charges. So before going to this, let us understand what do you mean by many point charges, field due to many point charges. Let us consider a point P. Let us consider a point P where you need to measure the electric field intensity. So this is the point P that the electric field intensity to be measured. Okay. So which is influenced by n number of point charges. Which is influenced by n number of point charges. Let us have these many point charges. Okay. And Qn. So on up to Qn. There are n number of point charges. So we need to identify the electric field intensity at point P influenced by all the n number of point charges. Let us consider the distance between this point to this point is R. Okay. Let us consider the distance between each of the point charges is consecutively R1, R2, R3, R4, R5, R6 up to Rn. Distance between point P and each of the point charges are considered to be R1, R2, R3 and so on up to Rn. The corresponding charges are Q1, Q2, Q3, Qn. Okay. So how this electric field intensity at point P is measured? By influencing all these point charges. In this circumstance, we have to go for superposition principle. What do you mean by superposition principle? When it comes into picture, superposition principle says that whenever multiple sources are available, the overall outcome from that multiple sources is equal to the algebraic sum of all the individual responses. That is called superposition theorem, superposition principle, right? So I'll repeat. So whenever the multiple sources are available, the resultant outcome from all the multiple sources is equivalent to the individual responses. In this case, so individual electric field effect at point P is equivalent to the sum of all the electric field intensities influenced at the point P. So that is the equivalent electric field intensities are E1, E2, E3 up to En. Got it? So the distance between Q1 and P is R1. Distance between Q2 and P is R2. Similarly, the electric field intensity at P due to Q1 is U1. Electric field intensity at P due to Q5 is E5. Okay, electric field intensity due to Qn is En. So the overall electric field intensity produced by all these point charges is E. That is, according to superposition principle, E is equal to E1 plus E2 plus E3 so on up to En. This is what superposition principle says. So overall response of the system is equal to the individual algebraic sum of individual responses. So that is, the overall electric field intensity at point P due to all the point charges is equal to the algebraic sum of electric field intensities contributed by each of the point source. Now coming to the mathematical equation for the same, we know that E is equal to Q divided by 4 pi epsilon naught into R square, right? So if we represent it in the vector form, then we will get AR cap. Okay, so if we have the unit vector for each of the point charges, then the unit vectors are represented like this. So for R1, A cap R1, A cap R2, so on up to A cap Rn. These are the unit vectors corresponding to each of the point charges towards point P. Okay, so this is the general equation. Okay, so if I write the equation for E1, then this becomes Q1 divided by 4 pi epsilon naught R square into A cap R1. For E2, then this becomes Q2, this becomes R1, right? So Q2 divided by 4 pi epsilon naught R2 square into A cap R2. So on up to, if I write En is equal to Qn divided by 4 pi epsilon naught Rn square A cap Rn. Okay, so after getting these equations, if I apply superposition principle here, E is equal to E1 plus E2 plus so on up to En. Substituting these equations into the above equation, E is given by Q1 divided by 4 pi epsilon naught R1 square A cap R1 plus Q2 divided by 4 pi epsilon naught R2 square into A cap R2 plus so on up to Qn divided by 4 pi epsilon naught Rn square into A cap Rn. So by looking at this equation, we have seen the denominator term is common in all the equations, right? If I take it out, 1 by 4 pi epsilon naught is common from all the equation, then this becomes Q1 A cap R1 divided by R1 square plus Q2 divided by R2 square into A cap R2 plus so on Qn A cap Rn divided by Rn square. So by looking at this equation, we can easily reduce this equation by using summation, right? So which is equal to 1 by 4 pi epsilon naught summation I varies from 1 to n. See, if I use this summation to reduce this equation into single form, so I varies from 1 to n. 1 to n Qi by Ri square into A cap Ri. This is the equation, general equation for electric field intensity due to many point charges by applying superposition principle. By applying superposition position principle. Moving on to the next topic in the same category, field due to many point charges. So the next topic is field due to continuous distribution of point charges. Why the name continuous comes here? So let us understand what do you mean by continuous distribution of point charges, then go for mathematical derivation of this. Okay, so these are the point charges which are arranged in this fashion. How do you call this arrangement? This is called discrete point charges, right? So the arrangement is discrete. Okay, now coming to the second example, you can easily identify the distinct length between each point charges, right? Distinct length between each point charges. Hence, this kind of arrangement is called as discrete arrangement, right? So coming to this next arrangement, second arrangement. What do you call this? So these are the point charges which are arranged in linear fashion with equidistant space. We can easily identify the distance between two point charges, right? So here also we can identify the distance between two point charges. Then coming to the third one, see, this is the point charge, and again one more point charge which are arranged in linear fashion. Now in this particular arrangement, can you able to identify the distance between two point charges? No, the distance between two point charges is almost zero. Hence, this kind of arrangement is called as continuous distribution of point charges. Got it? So, under this circumstance, what is the electric field intensity obtained at that point P to be calculated? So, under that circumstance, we have taken this particular area. Now, let us consider a finite area. Let us consider finite area where the charge distribution is continuous. That means in this particular finite area, the number of charges are infinite. That is the meaning of continuous charge distribution. Got it? So in a finite area, the number of point charges are infinite, then the resultant is called as continuous distribution of point charges. So the resultant electric field intensity at point P due to the infinite number of point charges to be calculated. Okay. So in order to do so, we have to use the same equation again, right? So under that circumstance, the charge at this particular differential area is delta Q, because very small charge has been considered, hence it is taken as delta Q. So out of this area, we are considering only the elementary part. Hence the charge at this elementary part is delta Q. So electric field intensity at point P due to this elementary charge delta Q is given by elementary electric field intensity is equal to elementary charge divided by 4 pi epsilon naught into r square into a cap r. This is the equation, right? Okay. This is the elementary electric field intensity at point P due to a small charge delta Q. Okay, so the objective is to find the electric field intensity at point P due to infinite number of point charges. That is the whole objective. Now this is the equation which gives the electric field intensity at point P due to only small charge delta Q. Now we have to set a limit in such a way that we can integrate all these things. That limit is as this small area, as this elementary area considered tend to 0. This is the limit we need to consider. As the elementary area considered tend to 0, then delta E or delta Q becomes differential parameter dE and dQ. That is, delta Q becomes dQ and delta E becomes dE. Got it? So, coming to the next part, according to this particular limit, so the equation can be rewritten as dE is equal to dQ divided by 4 pi epsilon naught r square into a cap r. This is the electric field intensity due to a small charge. Then resultant electric field intensity due to the entire infinite number of point charges can be obtained by integrating all differential charges, differential electric field intensities. That can be done by using this equation. E is equal to integration from dQ divided by 4 pi epsilon naught into r square into a cap r. Since 1 by 4 pi epsilon naught is constant, we can take it outside, then this can be written as dQ into a cap r. This is the equation which gives the electric field intensity due to infinite number of point charges. Understood? Coming to the next topic. So, with the understanding of previous one, field due to many point charges, let us move on to field due to line charge. In the previous case, what we have seen is, so inside a finite area, the infinite number of point charges are distributed. So, by using all those point charges, we have identified the electric field intensity at a given point P. But here the scenario is different. So electric charges are distributed in a linear fashion on a charged wire. Let us consider a charged wire where the electric charges are arranged in this linear fashion. Let us consider the length of this wire is L. So out of this length L, we need to calculate the electric field intensity at point P, which is contributed by all the charges along this line L. Okay, let us consider the differential length delta L, a small length delta L, which is represented by M. Okay, delta L is the small length along this line L. Okay. So field intensity at point P due to this line charge is calculated by using electric field intensity. So that is rho L due to line charge is equal to delta Q divided by delta L. Charge per unit length. Line density, surface density comes here. Here electric line density is equal to charge per unit length. See, this is the charge at this point delta L. Delta Q is the elementary charge present at this particular area delta L, particular length delta L. So therefore density of charges is given by electric charge per unit length. Okay, coming to the electric field intensity at this point P due to this elementary length can be assumed as in the previous case, that is, as delta L tends to 0, then delta Q becomes dQ, right? In the previous case also we have considered the same assumption. As this elementary area tends to 0, then this gradient operator will be converted into differential operator, that is delta Q tends to dQ. Therefore elementary electric field intensity due to dq is given by dE is equal to dq divided by 4 pi epsilon naught r square into a cap r. So the overall field intensity at point P is given by E is equal to integration of dE, right? In the similar fashion, we can write integration 1 by 4 pi epsilon naught into dq divided by r square into a cap r. In the next step, if I replace dq by rho into, so see here, this is dq by dl, okay. Similarly, we can write it as 1 by 4 pi epsilon naught integration from dq can be written as rho l into dl divided by r square into a cap r. So this is the electric field intensity equation for line charges. Similarly, for surface charge, the area is considered is delta S. Delta S is the small area we have considered in this particular surface. Okay. Surface charge density, that is rho S, is given by elementary charge per unit surface. Elementary charge per unit surface. Okay, this is represented by rho S. As the same assumption holds good here, as delta S tends to 0, delta Q becomes dq. Okay, the same equation holds good, which is given by dq by ds. So dE is equal to dq divided by 4 pi epsilon naught into r square a cap r. Similarly, the overall electric field intensity due to surface charge is integration from 1 by 4 pi epsilon naught is common, take it outside, constant. So into dq divided by r square into a cap r. If I substitute dq is equal to rho s into ds, then this is integration of surface integral. So rho s into ds divided by r square into a cap of r. This is the electric field intensity due to surface charge. Understood? These are the two mathematical models for line charge and surface charge intensity, field intensity. Got it? Okay. Continue to the last topic of this session, that is volume charge density, volume charge distribution, right? So consider the finite area under this. So we have to consider a volume of charge which is a three-dimensional one. So you need to have the special interest here. So in the previous two cases, under this line charge and surface charge, so the charge area what we have considered is two-dimensional or one-dimensional, but here it is a three-dimensional one. We need to consider volume of charges, right? So we need to have three-dimensional area. So then volume charge density is given by charge per unit volume. Line charge density, what we have seen in the previous case, is charge per unit length. So our surface charge for two-dimensional is charge per unit surface. So that is what we have taken. But here also, so volume charge density rho v is given by charge per unit volume. Okay, dq by dv. So electric field intensity at point P due to the elementary volume, so delta V, due to the elementary volume, delta V is given by delta E is equal to delta Q divided by 4 pi epsilon naught into r square into the unit vector AR. We know that as per the limit, so delta V tends to 0, delta Q becomes dq and okay, then and delta E becomes dE, right? Substituting into the above equation, then dE is equal to dq divided by 4 pi epsilon naught into r square into a cap r. Okay. So then overall electric field intensity E is given by integration volume integral 1 by 4 pi epsilon naught into dq divided by r square into a cap r. We know that dq is equal to rho v into dv. So overall electric field intensity is equal to 1 by 4 pi epsilon naught into volume integral dq can be replaced by rho v into dv divided by r square into a cap r. This is the equation for electric field intensity due to volume charge. But now we need to consider one more factor here in all the three topics: line charge, surface charge and volume charge. Let us recall the equations for all the charge distribution. That is, E is equal to 1 by 4 pi epsilon naught into integration from rho L into dl divided by r square into a cap r in this particular thing. E is equal to 1 by 4 pi epsilon naught into surface integral rho s into ds divided by r square into a cap r for surface charge distribution. Then for volume charge distribution, E is equal to 1 by 4 pi epsilon naught into volume integral, so rho v into dv divided by r square into a cap r. Here one more approximation we need to consider. If the length of this, if the size of this volume is infinite, the length of this charge is infinite, the surface area of this charge is infinite, then this constant, this rho L, rho S and rho V becomes constant. The length of the surface is infinite means rho L becomes constant. The surface area becomes infinite means rho S becomes constant. The volume area becomes infinite means rho v becomes constant. Since these becomes constant, so we can easily replace this equation by rho L into integration from dl by r square. Here also rho s becomes constant, we can take it outside. Here also rho v becomes constant, we can take it outside. This is the resultant equation for all the line charge, surface charge and volume charge distribution of point charges, due to which electric field intensity can be identified. Understood? Okay.